You might have seen some of my other videos on YouTube and found them a bit confusing. That's why I thought it is a good idea to give an overview upon the topic of laser prism scanning. My name is Rick Starmans and I've been working on this technology since around 2017. And I started out with the module on the top left. And this module used multiple lasers which were moved by a rotating prism. And the work for this module was done, was sponsored by the Dutch government. I improved this module by simplifying it and only using a single laser and a single prism. And that module is shown in the middle. And I actually made successful exposures with that module. Now, this module was quite hard to assemble, so that's why I decided to integrate the motor to move the prism inside the printed circuit board. And I used an invention from Carl Bugia for this. And that module is shown on the top right. And actually now I'm able to do that successfully and also stabilize the laser. The presentation is organized as follows. You should be able to click on these sections in YouTube so you can go to a section directly. So to recap on the process, what I have a laser module, and here you see an older version, and basically you have a laser which projects through a prism, and that creates a line. And then by moving the stage or by moving the substrate, so this plane under the laser, you can expose a plane. And now on this plane you see a white sheet of paper, but of course you could put some photopolymers there or a printed circuit board. And then by exposing multiple lanes, you can extend the area of exposure. Now, there are also other ways of doing that. And that is by combining two prisms. So using that you could also form a 2D image. And this was done in one of the first thermal imaging cameras. And actually this technology is still used today in LiDAR systems. For instance by companies such as the Tremble X10. But this process I will not discuss today. So I will only focus on this laser modules which are moved over stages. Now, applications. What you could do, and that's also what I've shown in the video, is you could make a printed circuit board. And then I don't mean you can make the vias, but I mean that you can make these tracks, right? So you can make a very precise exposure, and then using several chemical processes, you end up with a board with copper tracks. Now what you could also do is you could sinter powders. So there are like selective laser sintering powders like nylon, and if you expose them with an infrared laser, they sort of glue together. And for that you would have to change the laser in my system, but this should be very doable. What you can do with the current laser, which has a wavelength of 4 or 5 nanometers and is blue, is you can also solidify photopolymers. Now, the laser width or the exposure size, and we'll go into that further on, is around, say, 1 centimeter at the moment. So if you want to expose larger areas, you have to combine multiple lasers. And that's also why in the beginning modules were developed with multiple lasers. And other ways, of course, just doing multiple lanes and go over the part in a snake-like pattern. But what I want to highlight is that there are a lot of parts which can be exposed at once because there are a lot of smart parts. And you have to think about, for instance, jewelry, which is first made in plastic and then via casting metal comes out. You can also think about Lego bricks or small printed circuit boards or even markings, barcodes on products. So I think also for in the small parts and for single exposures there are a lot of applications. Now, let's dive a bit deeper inside the optics. If you make a system, you typically have a manufacturing error. And here what I draw is you have a mirror, which is denoted by the black line, and it has a manufacturing error of alpha. So we're uncertain about the position of the mirror with alpha. And that gives a total deviation of 2 times this angle. Now if we have a prism, a quartz prism, and we have a manufacturing error of alpha, so we don't know how straight these are within that angle, and we operate at 405 nanometer with quartz, so our refractive index is 1.5, then our total deviation is 0.5, this angle. And as such, quartz prisms are 4 times more accurate than mirrors. So that is a crucial relation. Now, what you might have seen is that what I do is I use a prism to move a focused laser bundle. So I have a laser bundle, which here is parallel and then is focused by this lens into this point, and then by adding this prism, the focus point moves away from the prism with this relation. What also occurs is that if I start to tilt that prism, so if I start to rotate it, I get a deviation orthogonal to the scan line, and you see that my angle of incidence is the angle of the transmitted ray, so they are parallel, and this is very crucial if you start to stitch exposures, and also it's very crucial in keeping the spot uniform over the line. And what you can also see is that there is a nonlinear dependency between the deviation and the angle. Now for the lines I currently use, which are about 1 millimeter, the speed alters within 10%. So I change that, and you can increase the efficiency of your, or the duty cycle of your laser prism scanning by adding more facets, but I've only used 4 facets to keep it simple, but that's something you could do. And what I now currently do is by modifying the laser driver, I can keep the exposure uniform over the line. But also in practice, a 10% difference in exposure is not a big issue. Now, as you might be familiar with laser scanning, you know that there are also other techniques for moving a laser bundle. For instance, what you have galvo mirrors. So these are mirrors, and they are tilted backwards and forward, and people shine on that with a laser, which is done by Formlabs. And then Formlabs also uses a scan lens to form a scan line. Now the disadvantage with galvo mirrors is that at the end of the line you have to move backward. And even if you can do this fast, your speed will be not uniform over the full scan line. So that is an issue, and that's why other companies such as Desktop Metal, which recently bought EnvisionTech 3SP, they use a rotating polygon mirror in combination with the scan lens and f-theta lens to form a line. And because this mirror does not have to change direction, it is much faster, and the scan speed is more uniform. But a disadvantage of rotating mirrors is that you need this 3-element scan lens, and you need to bring that in the machine, you need to align it, and also these scan lenses come not for free. So this is a more expensive solution. And in my solution, and that's why it's crucial, you only need this laser diode, you need to focus it, but you need to focus that here as well for EnvisionTech. And then with the prism, you can form a scan line. And as you see, I use a photodiode to determine the position, to accurately determine the position of the prism. Now what you also see drawn here are 2 cylindrical lenses. And that is because laser diodes typically have an elliptical spot. So the exposure area is, say, 1 by 2 millimeters or 1 by 3, or well, it depends a bit. And then you have an elliptical spot as a result. And these cylindrical lenses, they make it a circle. And what they would also do is they will remove some of the errors due to incorrect mounting of the prism. And I will go into that on a later slide. So, and then we have that, of course, the scan line of prisms is smaller than reflective polygons. And we have a 90 degrees of incidence, and this is typically not the case for polygon scanners unless you use an even more expensive lens, a so-called telecentric lens. So this system is much cheaper for a lot of applications and is also yeah, smaller and simpler. So as I said, is here what you see is you see two cylindrical lenses which are not needed, but I use them sometimes in my simulations. So this is a simulation. Here you see a prism which is slightly rotated, and then here the laser hits a mirror and then hits a photodiode. Now if you rotate this prism, of course the position of the laser bundle changes. But if you just move the prism in X and Y, nothing happens. So the position is not affected by a translational movement. And that is why I have the photodiode after 2 refractions. What I could also do is I could say, okay, I have light coming in, so it hits here by a cylindrical lens. And then my light is refracted, so part of my light will be transmitted, most of the light, but also part of the light will be reflected, and then reflected again, and then transmitted. But if I then do a horizontal move of my prism and keep the rotation angle constant, my position does change. So that's why I cannot put my photodiode at another point in the box. Now, some of you have read my blog probably, and in this blog there is also an obscure mentioning of more complex or advanced prism designs. So what is key is to understand here is that so far I've been talking about prisms where the rotation axis is orthogonal to the laser line. But if this were not the case, then the laser would sort of increase. So if this is your prism here, and I've made it 2 colors, but so if this is one prism, then if it hits under an angle, yeah, of course it starts to rise with respect to that prism. So it enters at a different height inside of the prism. And that's why these facets will never be seen by the entry point. So these are sort of exit facets, and these are sort of entry facets. And that allows you to alter that facet to further optimize the exposure. What you could also do is, of course, make a groove here. So your laser is pointed upward and then pointed backward here. So there are, what I want to point out here is that there are possibilities for more advanced prism designs which have not been studied. Now, a complication when you start to manufacture a system is that there are tolerances. So the thing what you want it to be, your system, that's also not always realized in reality. For instance, you have vibrations, you have misalignments, and you're interested in what kind of aberrations does that result in. And as such, I have to test the quality of my system. And here you see a setup how I do that. So I have a laser which goes through a rotating prism, and here it's not rotating, of course, and then it projects onto a camera. So I use a CCD camera, and I don't have a lens in that camera, but what I do is I directly focus my laser onto this camera, onto these chips, so that I know that I have, so that I count a number of pixels and then determine the laser spot size. And on top of that camera, I use neutral density filters to filter out if there's too much light. Now, and then if the laser is moving, you get lines, and then you can also turn them off into these lines. But then you will see, so for instance, here you see that there are 2 lines which are probably on the same place. If it's a 4-facet prism, so 2 facets end up at the same position and 2 other facets end up at a different position. So you see that there is a cross-scan error, an orthogonal error to the scan line, and not all facets end up at the same line. And this is an issue because if you move your stage at a constant speed, you want each line to be next to each other. So it's quite hard to compensate. The only way you could compensate this for is by decreasing your speech and doing multiple exposures. But we'll go into that later, but then you'll need to also know which facet you're using. So you have to know the number of your facet so you can correct for that. Now, what's also an issue with laser scanning, so a challenge you can face is that, for instance, say you're projecting a dot. So here we have 4 dots. So we see that 2 dots end up at roughly the same position. We see that we have some cross-scan error. And then also we see that one of these dots or one of these laser spots doesn't end up at the same position. So we see that there is some jitter, so there is an error parallel to the scan line. Now in practice, this error can be compensated quite well with the photodiode and correct timing. And this is in practice rarely an error. That is not really an issue at the moment. Now, if we look at aberrations, one of the things you could possibly do wrong is put your prism at an angle with respect to the rotation axis. Now, and then if you rotate it, as in this figure, so it starts to move tilting upward. And if you project a laser through this, now it would, in this case, actually exit at the middle or something. So it would work very different, and it wouldn't work at all. But if this would be less severe, it would still exit at that point. But if you then tilt it, you also make a cross, a movement orthogonal to the scan line, and that is an issue. So the mounting of the prism has to be correct. Now, as I've shown, there are solutions for incorrect mounting. What we have to remember is that if the prism is perfect, so if opposing facets are perfectly planar, then we know that all the rays, all the exit rays, will be parallel to the incident rays. So we have a group of parallel rays. And then if we put a lens, we can still focus it into a single point. So this would remove these errors from the mounting if we assume the prism is perfect. Now, if you place this lens after the prism, it would not work, because it would also work for this direction, which are also a bunch of parallel rays. So we have to split the lens into its 2 components. So we have a component which is parallel to the scan lines, which is done by this cylindrical lens, and we have a lens which works orthogonal to the scan line. And this lens will filter out the mounting errors. And the combination of these 2 lenses, because they have different focal lengths, so this length is longer than this length, this combination will also remove your elliptical beam. So this system costs a bit more, because these lenses cost in total €100, but it will remove your errors for mounting, and it will circularize your laser bundle. Now it must be said that, for instance, companies like Formlabs, they don't circularize the laser bundle. And I also don't think EnvisionTech circularizes the laser bundle. So this is this would give you really advanced optics. Now, there can be more issues with your laser prism scanner. For instance, the opposing facets in your prism, we've assumed that they are parallel. So what you want is you want opposing facets to be parallel, and you want that all the facets point in the same direction. Because that could also be an issue. They could be parallel but still moving upward. Now, if you have say 2 opposing facets and they don't point in the same direction, and they for instance cross, and then your incident angle will no longer be in the same direction as the transmitted angle. Now in our case, we know that the way these are not planar, these 2 facets is very small. So we know that the angle A is very small. And if the angle A is very small, then we know that the deviation, which is this angle, is proportional to this formula. Right? So that is an issue. And this error is actually quite hard to compensate for. So we cannot use the cylindrical lens technology, although it will reduce it a bit because it reduces the focal length, but this will still be an issue. So to summarize, so we talked about jitter. So jitter could be that there are other deviations in the prism which gives a problem parallel to the scan line. Now we could detect the start of the facet with a diode, and we can use a correction error. For instance, if we know each facet, if we know the number of a facet and the aberration of a facet, and this will not affect the throughput. Now, if we have the cross-scan error, a solution we could use, even if the prism is very badly mounted, is we simply use a single facet. It's a very simple solution. Your throughput would reduce. You would only use one of the 4 facets, so you could increase the spin speed, but your throughput will be reduced a bit. Now, what you can also do is you can detect your facet and use a correction algorithm. Then you can use all facets, but you probably have to expose a certain spot on your line multiple times to have a certain uniformity. So that will reduce the speed a bit. Now what you can also do is you use cylinder lenses, and that will remove some of the cross-scan errors. Or you could improve the mounting and the quality of your prism. Now, so far we talked about the prism imperfections, but another thing you could have are vibrations. And vibrations are caused, there are 2 main causes of the vibration. One is that you are spinning, say, a wheel on an axis. Now, if this wheel is not balanced, and in practice it will never be perfectly balanced, then you will have a centripetal force on top of this axis. And that centripetal force will give you a deviation, and that will also give cause to a vibration, and that you'll see in your exposure. Now, what is also an issue is that in my case the prism is attached to an axis, and this axis is stuck through a shaft, and then of course the prism could move upward and downward in this axis. So there are also vibrations possible orthogonal to the shaft, and that could be a possible issue. Now, when I started designing this system, I thought, okay, I have to use something which already exists, because that will definitely simplify making such a system. So what I did is I bought a Ricoh polygon mirror motor, and these are used in laser prism printers. So you at home you also use, some people still use laser printers, and there you have these motors. So here you have a mirror with 6 facets, a hexagon. And what I did is I removed that mirror, I grinded off this axis, and I glued my prism on top of that. Now, and the guys from Ricoh, they have done this very well. So this base, they have the base and the shaft are really made well. So that's why my cross-scan error was quite low with this solution. And roughly what you have to take into account is that the planarity you have, so say your base is planar within 50 microns, is that your cross-scan error will then be 10 microns. In the case of the dimensions I have for a prism, and yeah, so in my case, and for a wavelength of 4 or 5 nanometers. And you can simply calculate this with the formulas I've shown earlier. Okay. Now, as you might know, is that I started to improve on my design by using my own motor. So the problem with the motor from Ricoh was that I had to add a lot of wires to connect to this motor. I don't have full access to the software, and as such, it's quite hard to scale. Also, it's not really made for my solution for my problem. So I thought, okay, I want to add this axis to my prism. So I could add this base, but then I would have to manufacture this base with high tolerances. So I thought, okay, why not use this prism? So what I currently do is I use a aligner, and then I push a rod through this aligner and with glue, and then with UV light I cure this glue. Now this glue will stick out from the shaft at some point. So that's why when I add the shaft, I add these grooves. So I'm sure there is no, it's not affected by this. And then if the shaft is not completely perfect, as my prism is perfect, it will not have a cross-scan error. Of course, in practice there are some other imperfections to the prism which will give it, but this should work quite well. And now, a further thing, what I have in practice is that my rotation is not horizontal but vertical. So in that case, the rod will simply drop out. And what I now have is, so I have magnets here, which are attracted by the PCB, which is below. I will show that in the next video. And then here I add a ferrite. And these magnets are pulled toward the ferrite, and that's why the prism stays in that position. And that works quite well. And this ferrite solution, I think it's also used by Ricoh. So that is nice. So if we look at the current solution in Freecad, so here you see the laser. Here you see some laser lines, and these are possible paths for the laser giving different position of the prism. But in this case, there is only one position valid, which is the straight line. And here you see the prism. Here you see a plastic part which is glued to the prism. Here you see a magnet inside this plastic part. Here you see the magnet missing. And here you see the shaft and the axis on top of the prism. And here you can see the coils in the PCB. And below this board there's also a ferrite, and then these magnets are pulled toward the ferrite. Now, and that works quite well at the moment. So now we can start to look at some of how well does this system perform. Of course, what you could do is you could say I can make a full exposure, but as I said, the jitter in practice is not really an issue, so you don't need to do that actually, although it gives more confidence by our customers, but in practice you don't need it. And what you basically look for is you look for the cross-scan error. So you make these images with the aberration setup. And in 2018, with 2 cylinder lenses and the Ricoh polygon mirror motor, I had a cross-scan error of 60 micron. Now, I thought, okay, these 2 cylindrical lenses will be quite expensive. It adds 100 euros to your system. And then also the cylinder lenses have to be placed in a certain position, which takes some alignment time. So that's why I also studied system without cylindrical lenses, and then you add on at a cross-scan error of 111 microns. And I made a successful PCB exposure with this system. And of course, the results for this depend on your distance between the camera and the prism. So if you're closer to the prism, it will work, this will reduce. Now, with my new mounting, so I also made some exposures. And there at a slightly different distance, I reached a cross-scan error of 160 microns. And what I really liked about this exposure is that you don't see vibrations. So the exposure, I have a video of that actually, but it's very static over time. Now, and then you can also wonder, okay, what are the aberrations? So you can look at multiple exposures without the prism moving. So you make, say, 2 exposures per facet, then move your prism, you make 2 more exposures per facet, then you stick all these images together, and then you can get an indication of the cross-scan error, and then you end up with this image. And as such, I concluded that my cross-scan error from the prism is around 120 microns. Now, I validated that system, and you can see that validation online. So I validated the system completely on the printer. This is an example of some of the PCB exposures which have been made. You see that the lines can stitch. You can find this image online. You see that there are some issues at lower resolutions, and you can also see that sometimes there is a bit of unevenness between these stitching. So there are things you could improve. What I mainly did this for was really testing if the concept of the technology is working. Now, with the new motor, which is integrated in the printed circuit board, I can stabilize the laser, but I've not made exposures because it's quite time consuming to do so. Yeah. So then finally, let's look at some feedback which was received by speaking to possible clients or people interested in these developments. So I spoke to a guy who sells jewelry in Turkey, and I told him, yeah, so why do you use lasers? And why does Formlab still use lasers where we have LCD or even DLP technology? And he's really confident that lasers give you this excellent surface finish. And for jewelry, if the surface finish is not perfect, you end up that you have to grind the metal, and that's time consuming. So for him, the laser surface finish is superior with lasers. There is also a lot of interest in selective laser sintering because you can put quite a lot of power through that prism, and lasers are quite nice here. So LCD is not really useful for selective laser sintering. So there is also quite a lot of interest in this system there. And as the technology is open hardware, and it uses quite interesting components like FPGAs and say printed circuit board motors, there is also interest from a lead user group on Hackaday. Now, there has also been negative feedback, and I thought it's nice to give an overview of that. So there's always this complaint about this short scan line, although this sort of reduces if you speak longer to the customer. But as said, this depends on the application. If you have small parts, the scan line is not short. There are mitigations with these complex prism designs, or you combining multiple laser modules. And what is also need to be said is that the deposition area of a fused filament printer, so in that technology you have an effective area of which is 300 micron, and as such much smaller. So my printer will be much faster than an FF printer. Another thing is that people complain it's not a complete solution. And then this is really done by choice. So developing hardware is very time consuming. Also, people want something which is of high quality and works. So that's why I really focus on this laser head. And I will stick to that focus for the future. Other issues which were pointed out, and that was with my earlier version, is that they looked at the bill of materials because it's open hardware, and people thought, yeah, it's still expensive. If you look at what Chinese ask for laser for LCD printers, is yeah, how can it be that expensive? And I think yeah, that is true, and that's also some of my focus. So I reduced the assembly cost by integrating the printed circuit board motor inside, or by integrating the motor inside the PCB. And what I will further work on, so I worked on that a bit, is I will remove the Raspberry Pi 4 and replace it with a microcontroller, say also from Raspberry Pi, which is cheaper and makes it easier for users. Then there is of course a lot of complaints about the ease of use. It is a complex video or complex technology. My videos can be a bit obscure. Also the explanation can be ad hoc because it's done in the moment. And I hope to mitigate that by improving the documentation using such videos as these, and also simplifying the integration with existing controllers. So what I really aim for, and now we're getting to the outlook, so my current aim is still to lower the entry barrier, so if we talk about price, but also in terms of assembly, and also simplify it, so there is more documentation and people are like, okay, that is how it works, that is how I might be able to use it for my application. And in the end, what I aim to do is I will design a single module, and as such the FPGA moves to the laser head, so you end up with a laser module, and you can control that laser module, say via SPI. So that should make it accessible via existing tool chains such as Smoothie and Marlin. So you would simply give some instructions, you would send some data to the laser head to store the path, and then it would start to work. Now I will not give an example on basis of these tool chains, but I will give an example on basis of a Raspberry Pi Micro, and may give a C++ class, so you can use that for your technology. And of course there will be some instruction videos. So that is the outlook. Now, questions can be added in the YouTube video. So finally, I want to say a bit more about the origins. So the project originates from the Dutch state. So I worked there around 2017. And basically the Netherlands is quite interested in printed circuit board printed circuit boards, and also the creation of printed circuit boards. And we studied the system then, which is called Cleo laser direct imaging, which was made by Carl Zeiss, which is a well-known optical company from Germany. And what they have is they had 9 polygons, and these 9 polygons were exposed by 288 laser diodes. And then by rotating these polygons, so these were mirrors, you could create laser lines. Now, if you then move this whole structure, you would end up with this shaded zone. So they would sort of all overlay. So by tilting these polygons, and that's also what you see in this video, you can increase the exposure size. Now, tree here is that, okay, we thought, okay, that's a very cool system, that could be very cool for innovation. We can get some money from the government from that to develop that, and so we filed for a patent, or the Dutch state filed for a patent, and the original target was the PCB market, and of course we had an invention which was this prism. So we replaced these systems with a prism, and then it would be much easier. Now, so the Netherlands invested, say, $1 million into it. This resulted in LDI systems, which focused on the PCB application, and that went bankrupt, I think, a couple of years ago. In the meantime, the 3D printing system was developed, and that has been ongoing up to now. So they still invest in that up to now. But there are some issues, because I did study this system in detail. So the first problem I see up today is that it simply violates Occam's razor. So you multiply lasers, which makes your system much more complex, because you have to align these lasers, and you have to solve all the issues associated. So vibrations, perfection of the prism, you have to have the same spot size, so you have a lot of issues there. And then the question arises, is why don't you use a single laser and a single prism? And if you would answer that, yeah, but there is no market for that, yeah, then why is there a market for that? So it would, in my opinion, simply make more sense to start with a single prism and a single laser, which reduces your cost. Try to sell that, and if that's really successful, you can go for this system. But if you use a long prism with multiple lasers, your scan line is shorter than if you use a single laser and a single prism, that multiple times. And so you end up with a shorter scan line due to this angle. So I would still not use it. Now, then what you also have is you have more vibrations, right? So you have an area between your lasers where you have quartz, because you need to connect these quartz elements. And if you start to spin that at high speeds, you don't want to spin a lot of mass, because that gives you vibrations. And we also talked about the centripetal force. We also talked about that sort of rises squarely or whatever with the length of your from the rotating point. So that is also more complicated in the system. Then you have to glue your prism at 2 points. So you have 2 endpoints, which seems to me harder than to glue it at one point. So we talk about the prism mounting, we talk about the accuracies, so you need to have at least 10 micron accuracies across the entire system. So I think there are issues, and as of now, I've not seen a successful system. The measurements which I did back in the day concluded that, you have these issues and they are hard. So I wanted to add one thing. Which is not said so far. So the patent, which is owned by partly owned by the Dutch government, it does not cover prism with a single laser bundle. And the reason for that is that in the original application they do speak about 1 or more laser bundles through a prism, but they did not provide more detail on that. And as such, the the patent office narrowed the scope and says, okay, you have a plurality of laser bundles through a prism. So that is quite key. And in the European patent, which is still ongoing, the claim is also that the lasers have to be parallel to each other along one of the facets of the laser prism scanner. There are a couple of other things in the presentation. I say somewhere that the scan line is 1 millimeter. Of course, that should be, it's 8 millimeters. Actually, it can go up to 25 millimeters, and I've used 12 millimeters in some exposures. And then somewhere I talk about the laser emission area being in the orders of millimeters, and that should be microns. Okay. If I have more issues, I will add that also at the back of the video. And thank you for your time, and have a good day.